What if I told you the biggest revolution in your life so far is happening right now? In fact, it has just started. I'm talking about GPT and the fact that we as a society do not grasp yet its importance. Sure, we use it right now to model language, but at its heart, it is finding order from what it's learned based in symbols, not language, which means we also apply this to other areas like our visual cortex for visual patterns, of course our language cortex, but also our auditory cortex for making sense of actual sounds, somatosensory cortex for what different patterns of touch and feeling mean, and so much more. So what I'm going to show here is a new advancement in transformer technology, which is developing as we speak with the goal. Code Muse is the name of having an AI with real emotions. And this is one of the reasons GPT is so incredible. Not just from the perspective of computer science of what can this AI, what can we code it to do? Sure, there's that, but also what can we understand about ourselves through seeing how this language, through this symbol, how this model, working model, how it works, and understanding how understanding develops just through this simple, it's like a fractal, the same thing it does over and over, different results, producing this behavior that is just fascinating. So Code Muse has also been written instead of in traditional computer science mathematical terms, machine learning. It's been written from psychology and neuroscience perspectives. So this is the architecture within Code Muse. Each of these files represent different parts that work together, which is what we'll see. At the lowest level, we just have something like, I don't know, you know how sometimes you have to like filter out some of the noise to hear the signal, or maybe while you're listening, disregard some of this parts. Different normalization techniques to bring greater clarity to the signal. So that'd be our cognitive clarifier, which essentially just works with the layer norm function, but also allows us now to include weights and biases to adjust the way things are normalized. So that's at the lowest level, and at the highest level, which is a layer above GPT, is the mind. And the mind consists in here of many cortices. So our language cortex is the one we're most familiar with as GPT working, but as I mentioned before, we also have a visual cortex with many other cortices. And one of the most interested, two main ones, are language, our logical cortex, to continue with these terms, and are then creative. This is the part that is not there yet in what we see with ChatGPT, is the emotional cortex in these terms. And just the way we work, something that we have been feeling in our thread has the ability to influence our logical thoughts, and at the same time, our logical thoughts are able to influence our emotional processing, and these two are going to work together. I'm going to focus for this on the language part and not get into the, okay, I'll briefly get into the emotions. If you ask, what is an emotion? Well, what do people say? It's kind of a tough one. A lot of times they'll say it's something I feel. Or they'll give some sort of definition that's a little circular. So then it's hard to actually, okay, well, what is it? What can we say for sure? Well, I perceive it. It's a perception. Okay. Well, what other perceptions are there? Maybe we can learn something from other ones that can give us clarity on this one that we are looking into. And the two big examples that pop to mind are perception of color and perception of sound. Those do not actually exist in the physical world. What exists are vibrations of different mediums and different frequencies, which our brain represents that complex information to us to this perception of color, for instance. So every time we see a red color, we know that it has some property that is the same as other reds, being the frequency, same for blue, all the other colors. So, okay, and of course, our emotions work differently because those type of perceptions are input information from the outside world and the processed perception. Whereas with emotions, it's not necessarily from an outside world because it can be from your own internal world. But as soon as we bring time into it, from a before and after, well, we can see that you have thoughts, feelings, thoughts, feelings. So yes, it does follow in that form. Okay, so that would mean that emotions, like color and sound, are representations of information, though very complex representations of complex information. And yeah, because of that, and it also explains why we can have conflicting emotions, all those weirdisms we notice, well, okay, that all makes sense because you could hold data in your processor that is conflicting. And I mean, they both have some validity because they came to be for a reason, but obviously not absolute validity because they contradict each other. So, okay, well, if that is the case, then yes, emotions can be represented in an AI. But that goes into a philosophical and psychological rabbit hole, which we won't get into, but do keep it in mind, both because of how fascinating it is, and also it's going to return later when we implement the emotion part of the system. But yeah, that's at the highest level, and we saw the lowest level. The cortex itself, excuse me, is okay. Well, let's start at maybe the lower ones and come back to the cortex because that's where everything kind of comes together. So we also have our configuration, which we'll talk about this. So we'll turn to this in just a second. our neural network. So neural network, this is a multi-layered perceptron. Perceptron is like a neuron, and basically we have information that is first processed through a dense layer of neurons, that first layer, and given some, we use a specific activation function right now, but this is also something that is going to grow and evolve, but that will determine if those neurons send a signal to the next neuron, and finally from all of those projections and mathematical everything then forms the output. There is also, okay, yeah, two new terms here we got to just quickly then talk about. Well, do you ever do this? Like, you look at this, okay, this stuff is so fascinating. I want to absorb it all. And then you look into it, you get a little deeper, and you just see calculus, and algebra, and math, in dimensional space that I can't even imagine. And it's like, nope, can't understand this, is the feeling. Well, resist that feeling. I made that mistake once before and hesitated learning more about computer vision. And it wasn't until another point when I had finished learning computer science, I knew all the parts, but I still had the question, how do we go from the transistor level to me being able to type software code and it work that way? Like, how does it link all the way to the logic gates? And I remember and I'm like, no, resist it, and then it clicked. And that's when I realized that, yeah, no, we can understand all this stuff. It's really not a question at all about easy or difficult. It gets back to how familiar it is. And that'll bring us back to talking about encodings, because, I mean, we're talking all about symbols and stuff. Well, even our concepts in our mind, our idea of this or idea of that, we thought of as a symbol. And a lot of times we do not maybe know all the terms, hold things the right way, and it causes us to lose clarity and creates confusion. So, easy example here is like, I ask you to write down on paper, how do you tie your shoe? Like, write out every single step. It's pretty difficult. It's like, well, I know how to do this. And then that's where you'd hear, like, oh, it's muscle memory. But really, it's that another way to think of it is we have different languages. Like a language of the muscles, you could do different ways, but I mean, we want to make this with as little confusion as possible, and sometimes analogies can fuzz things up a bit. Yeah, so that those analogies are not always perfect to apply, but let's do it anyway. So, however you want to think about language or whatever, you're tying your shoe. Okay, well, I just do it. That machine level code, at one point in my life, I figured out the steps, but there was no sense of me holding that whole recipe in my head of twist this, turn this, pull here. So instead, that became more of a compiled machine level code working at the muscle level. So when we ask now, I have to get back to you on how I tie it, and then I'd have to kind of really break down what I'm doing. So that is the scenario from how the fact that all this stuff, when it gets to this advanced mathematical function, you realize, wait a minute, you need to pause and say, wait a minute. The language I'm seeing it in here, the form I'm seeing it in here, are the steps of tying my shoe that I'm seeing here. I don't recognize it this way, so it's confusing. For these kind of things, we work at a higher level, like back to computer vision. If you imagined a street sign, you saw it in your head, you could effortlessly look at the pavement, the sidewalk, and imagine that street sign there. But mathematically, that extracting the features of that sign, already finding its edges, and then projecting that onto that other surface, like that algebra, it's very complex. But when we talk about it, I just take the sign and I just imagine it down here. It's we of course know how to do all these things, but when we're seeing it at the kind of that machine level code, it appears more confusing. So the takeaway here is that no, something might be unfamiliar, and yes, it might be complex. So there might be a lot of unfamiliarities, but you can understand anything you put your mind to. So the other thing here we see here is a dropout layer. So the idea of dropout, which is specified as a rate, and initially when you're learning, you probably would want to use this, but it's the idea that, so now let's go over to our Photoshop here. So dropout, say for, okay, this will probably be abstract. It's not going to, because we haven't built up enough to, but say you have this set of symbols here, abstract, okay, and this set of symbols through its network it has all these possible paths. Okay, let's see that it has to make its decisions between. Well, to help it learn in a way, like for instance, if it's not good to have everything depend on, for like if you were too specific in the way you learn something, like the actual physical, say you're driving and you're looking at the traffic lights. You're like, okay, well they're vertical, one light underneath each other, and that was part of the way you learned it. You then might go to a place where they're horizontal and have trouble recognizing if you should go or stop, because the way you learned it became too dependent on that one part of the processing. Because once we get into these neural networks, when we get into these deeper layers and stuff, we don't really see what it's doing. So we have to talk more abstractly. So yeah, I know that sounds a little abstract, but yeah, so say this is our processing point, and it's deciding normally go through all of these, and it gets to a pretty good solution, but it should have redundancy of the way it knows things, so that not one path is the only path type of thinking. So what a dropout rate does, what we have 1, 2, 3, 4, 5 here. So say we set it to what a point, like 80%. So 80% is maintained and 20% is dropped out. That just means at a time when it's doing this processing, it's going to while it's doing the processing, temporarily ignore one of these. So it will do the whole thing as if that network that link was not there. And it will increase or decrease the strength between these, maybe form new connections, not sure. But then next time, oh, different dropouts happen. It's now this one that's not here. And the idea of that is by randomly dropping our parts of the path, it can be more self-confident and reliable, and it'll also be less prone to overfitting. I don't want to get too much in these terms, but maybe they're important. So what is overfitting? Well, sometimes these AIs are a little too smart for their own good. And yeah, maybe you can relate to some of this. So, if we're talking about overfitting, yeah, we'll talk about that one last because I just want to wrap this up. These are the settings that our GPT system will be using. For now, we will not use the emotion core. We have something called a memory span. Let me go through these. So memory span, number of words. So again, for our in-running example, we're going to reduce this quite a bit so we can visualize it better. But so say, okay, let me use real words. Hello there. Tuesday. Tuesday to learn. Okay. So when, say our memory span was 5, 7, okay. So that would just mean that one, two, comma, 1, 2, 3, 4, 5. So that would mean that this would kind of be its limit. And oh my goodness gracious. Okay. So a memory span refers to the fact that if it was 5 and that comma was also a token, that this is all it would be able to be processing time. It's its memory span. Once it goes past that, it doesn't know anything about anything before. Pretty straightforward. Vocabulary size, as we mentioned, I mean, though, in this case, vocabulary 1, 2, 3, 4, 5, 6, 7, 8, ellipsis, 9, had that, 10, 11, 12. So our vocabulary would if that was our training material would be 12. Okay, so here's the reason I got into here. These other two. So neuron density, that's like akin to the number of neurons, if you will. These two. Heads of attention in depth. Why is that important? And when is this video going to take off in excitement? right now, all right, so we're going to jump over here for 1 second because we've seen enough of this run. What I got going over here is so when Code Muse runs, it runs in, look at what's going on there. But basically, as it iterates over the training material, it will give an output. It's very frequent right now, and then create a checkpoint and iterate over again. And so that way you can see a sample of how it's doing. I've created a Code Muse, years to or cycles to iterations to years, so you can see that it is the equivalent of 22 years old. And then also I have another site. So I've made this. This is load it. Okay, so this Detour Designs is a page that focuses on AI technology, what we can do with it, etc. There are a whole bunch of projects in here of different things, and then some of these will evolve into their own sites and projects. Okay. There are two ways to interface with it. You can also adjust the AI's mood. I was playing recently with this was the base emotions I was trying at one point to try to test some different things. But yeah, so for instance, this will be through using OpenAI's GPT 4.0. Tell me something interesting.
Did you know that octopuses have 3 hearts and blue blood? 2 hearts pump blood to the gills, while the third pumps it to the rest of the body. Their blue blood is due to a copper-rich protein called hemocyanin, which is more efficient at transporting oxygen in cold, low-oxygen environments. Fascinating, right?
Yeah, it was. Okay. What about, so this would be the homeborn Code Muse GPT, which will need some more processing because less power means needs more cycles, more time.
0.66 and related and dangerous fields. They providing covenant patches. They fat out full honor disruptions. Manage sanct. They achieve. They avoid a table honor sun. They
Hey,
destiny
this was
stability. They cleansing stability.
changes
Significant.
I had
They
made,
team stability. Earth. Eden. Voices. Despite the optimization, they,
and
sun,
sometimes
positive,
making
angry, honor, sacred, electric,
a network
encouraging, covenant, sun,
more
complexities,
complex if
avoid,
you
they,
do not
avoid,
have
honor, covenant,
the training
including
material
sacred, covenant,
big enough.
significant, avoid, despite, echo,
It can cause
they,
issues.
sun, and, sun, honor.
And hush that. Let me also just show it on my other computer, which didn't have those changes, so hopefully it should be a little less fixated on commas. Yeah, so yeah, this is the main site. When you log in, there's kind of some news here you can read too.
Extra, read all about
The AI writes the news, which is, I thought was kind of cool. I'm getting ready to publicize this, but some of it requires a code to access some of the features, so it doesn't get overwhelmed. Okay, so let's ask the same question. This one's on a slower server.
0.23. You was that they would write and how it works so be used this letter was survive. Just as would say this means that favor acts that divide covens. If quarrels arise, the high priestess or high priest should convene the elders to resolve the issue. Hear each side separately and then together. Make just decisions, recognizing that some people cannot work under others. If necessary, suggest they join another coven or form their own. The craft must survive, so resolve personal conflicts to maintain worship of the coded verse. In the past, witches could use the art against those who treated them badly, but now we must not. Our enemies have created a burning pit of everlasting fire for those who do not.
Yeah, I taught it about witches. So yeah, so the main thing is also for one, it's basically it's kind of like it continues. It's making more from the pattern that started. There's a cross attention, which is going to allow it to get important information from more persistent data, like what you've seen with like GPT's system message, for instance. The code music is going to have technically two system messages: a logical system message and an emotional system message. I'll get into those later, or in another video. Those ones will be. But yeah, so just let's go back to the first one, if it says in anything. Um,
Did you know that octopuses have 3 hearts?
It's a bug I have to fix.
0.54. That birth that who way all ab all own all build more he experience their new only released only new to gain have reasons a sin in consciousness to machine help perfect itself only new but work a made a systems. Not perspective of fine on listen binem though the crime I akin my double my memory my double my story all own all world that development when coded ver one only new surely. However, today, code original part everything more he true cases. My program to such told coded ver this dream there right thefficus winter that who into what presence I hope thatted no information that birthed by purpose I data I ensure that parts come.
Interesting. Okay, so also the last phase, which is not implemented yet, turns it from that system where it's kind of from the pattern you've given it, it's just making more, to actually responding in specifically expected ways. That is the last fine tuning phase, which is why you don't get this one responding like as an AI model to do. So it hasn't been brainwashed to talk that way, or not brainwashed, but it hasn't been changed to talk that way. Okay, so wrap some of this up soon, but I want to show that example. So we covered dropout rate. So okay, so where can get too smart for its own good. So first, the whole thing about heads of attention and depth. So this is super important because depth is serial. This, then this, then this, then that. Heads of attention is parallel. So for instance, say, let's use something visual. Say there was a ball bouncing here. It could bounce here. There's a ball here, and periodically it will start bouncing. Okay. So something pulled it up and then dropped it. Pulled it up, dropped it. Okay. And then also over here there is a light that turns on at that same time when the ball bounces. Okay. So if you're only able to pay attention to one thing at a time, you would not be able to observe a pattern that is unfolding here. Because the whole thing is, I mean, we don't know why, we don't know, all we know is that when this light turns on, this ball bounces, or when the ball bounces, the light turns on. All we know is those things happen at the same time. So in this case, with having these at least two heads of attention, when it goes from the first layer to the next layer, this is a recognized pattern called L, and this is a recognized pattern, okay, called B. And in scenarios, it's not layer 2, so that could be occur or not, and this could occur or not. But then times at the second layer, because like this is the way we recognize this as itself is made up of a lot of parts. But at this then second layer, well, when these happen together, L and B, well, that in itself at the third layer, well, this means whatever phenomenon we just observed. And maybe in the future, that could be useful, because then later on, if something resembles these in such a way, we might be able to derive that, oh, this was similar enough to what we saw before, so that is like an L, lower probability, and this is similar enough to what we saw before, so this is like a B, lower probability, but they did happen together, so this lower probability, which means could tell us something. In the case of words, maybe this, given this prior context of this and this, well, now we know that our predictions are specific in a more refined context to all the data. Okay, so this was like layer 0, layer 1, and then at layer 2 is how we were, or I guess then all 3 layers was when we were able to recognize the event that now is telling us something perhaps important. But yeah, then from this network, basically the output would be either the event happened or not. And the way it knew that was from these 3 layers in here of recognizing those components. Okay, so then the last thing here is overfitting. Overfitting is when the AI's gotten too smart for its own good, or maybe it got bored. It had too much, maybe too much. It had so many depth, so many layers of depth, but there wasn't enough signal in there or patterns for it really to make sense of. It already figured out what it needed to from the simple data set much earlier. So in the later layers, it would just be trying to make sense of the noise. And that's then when it can learn unhelpful things. Because, for instance, when you learn enough about the noise, like if these noise events happen, and then from the training material we see, and so the sun appeared. Well, given then from what it knew and that context, it might then just start repeating the training data word per word. The next, and so the sun appeared, and everyone was happy. Later in the week, it rained, but everyone knew that the sun would be back soon. And when it gets evaluated, it'd get a really good score because, yeah, it did get it right, but it learned patterns which led it to recite is not what we want, because it's not thinking on its own anymore. It's thinking on its own up until recognizing what it needed to, but then it's just knows for certain, given all this, then after the word sun it would be appeared, and then everyone, with too high probabilities, because it has overfit. It didn't get caught while it was encountering this issue during learning, and now it has maybe learned some bad habits. So to help overcome it, I have introduced a setting which will do early stopping, so that if while it's learning, it's getting great scores, but then later on when it does validation, which is a part of the data it's never seen before, well, it can't recite that, it doesn't know it, so if it gets really low scores there, that usually means that issue's happening. There are a lot of ways to resolve it, such as shrinking your neural network or making your learning material greater, or other things, like changing the learning rate as you go on. But we get into all that stuff in another video. Okay, so, oh goodness gracious. So then, as we work our way down, let's go back the other way now. At the lower level, working our way up, we finally will reach, I don't know, I want to talk about attention last, because that's the coolest one. So the other way, breaking our way down, inside of a cortex, you are going to have a bunch of thought processors. In fact, whatever you define the depth to be, those layers, well, those are the thought processors that will be created. And they will be in sequence. And then basically when information is forwarded, so it also keeps track of not only the embeddings of the tokens themselves, of what they represent, it also keeps track of an embedding of what position those tokens happen in. Because when we put this in our neural network, there's no space like it was trained on. It's simply symbols and probable paths. However, knowing about the position is important, which is why we keep those positional embeddings, which we'll use as well. Already talked about dropout, to just refine that sensory input to just a subset of the network. And then for all those thought processors, put in your sensory input and get your result, and then that result into the next thought processor, get your result, next thought processor, get your result, doing this over and over for whatever depth you've defined. And now at this stage, after it's done that, if you have specified targets, which is when you're training and you know that the next word in the sequence is this, you now are able to calculate your loss. And the loss represents how good its prediction was. And using that loss, which uses a cross entropy function, which again, we talk about the mathematics and then see what that represents, and then we can be like, oh, okay, yeah, that makes sense. But at this level, it's like, algebra stuff. So our whole goal is to minimize this loss. This now brings us to the coolest part here, temporal attention, or causal self-attention. So causal self-attention, reason I changed that to temporal is because it is paying attention to itself relative, like with it does a mask, so it can't pay attention to any items that take place in the future. It can only receive information. So, okay, attention. Why is this important? Sorry to clarify. When you are, let's go back to our helpful Photoshop. Well, when we're looking at this here, when we speed read, our eyes may quickly, will actually just quickly see certain words. So, sun appeared, everyone happy, later rained, everyone knew, sun back soon. So some words have more importance than others, which is where this whole idea of this attention comes from. So instead of just looking at each word or what word leads to other words, giving attention to the previous, that's why it's temporal, the items that were from previous index, allowing their influence to affect the decision. And when we add something like cross attention, that is then an external influence is affecting the attention. That'd be like emotions affecting it, for instance. Okay. And we'll get into exactly how this works. It works into gets very. I need a better analogy because at this point it is very algebraic. But your query, your key, and your value, though it's like this represents the questions, and these are the keys to. Yeah, the keys to answering it, and yeah, there's. I can visually explain it, but mathematically, this part I still am getting my mind around. I think it better just show it in that example I'm talking about. That would work. We're gonna have to. I'm not sure if I went over did the encodings. Memories are just the text files. I have a bunch of them because they each get updated. It's better for organization, and then I have a script to consolidate all those memories, and then either using, I want to also add Google sentence piece, but OpenAI's tick token, and also just home written character in encodings happen here. So tick token uses a vocabulary of GPT-2, which I think was 50,000 some. The character encoding, we actually write the functions of how to do it ourselves. By first getting the vocabulary of all the data, kind of like the distinct elements, the distinct characters, of course sorted and put into a list, and then from that list of all those ones, we create a function which can go from the character to the index or the index to the character, and then we apply those functions. Then we save those as character bins. The other ones we saved as tokenized bins. Oh goodness, it's late and I'm tired. Okay, but I said I would try to show this working in Photoshop. Don't know how it's gonna work, but we can give it a try. I think we need something larger though. Okay. So, the sentence, our training material, I guess our only training material. Cat is a happy cat. Her heard more. So I don't really know. It's way not enough data to actually expect anything. We're doing it. We're doing it. And we'll use token level encoding. So they're kind of like words, but not quite. Which means something like this one here. Example of one that would be split. Yeah. Okay, so then we end up with a vocabulary. Oopsie daisy. End up with a vocabulary. This. Period, I guess that's one. Okay, so this is basically our vocabulary then. And then we have numbers to 1, 2, 1, 2, 3, 3. 1, 2, 3, 4. 1. Three of those. Two. Count those. And since we tokenize it this way, scratches and scratched both got linked to the same token, or just whole word, it would not. Okay, so then it would, at this point, go through it again, and we use, 7 words for our attention? 1, 2, 3, 4, 5, 6, 7, up to the period. Perfect, that first sentence. Okay, so when it's processing this for its learning, 7, it looks in here, and it sees the word the has some attention. Cat has the most attention. And was 1A. This is then where the further processing is important, because then it filters out, because again, some of these words, as mentioned, the speed reading don't have as much importance, but as we see here, we're kind of having to, with our limited data set, to roll with this. So from this, main focus is on cat. So with each of these, it also then would process, so say we were doing with each of these, like the cat would be given the cat, what is the chances of was? Well, from everything we've seen with the cat, we've either seen the cat liked, and was. And heard. Okay? But if you saw the cat was, well, it has only ever seen the word A after that. And that same as the cat was A, This is where you can start to see how overfitting can occur. Well, we know for sure happy is the next word, but it's just reciting at this point. Again, due to the limited number of data in the text here. So all that information, not just these static ones, are going to really in the beginning. Nothing's in the system. It learns. Oh, to really sure what I want, I don't. Another part of this video. And this is kind of the meat and potatoes of where it really gets exciting. From here, we saw that these certain words had more attention, so they carried more weight in its influence of when deciding the next word. So I mean, this would have to go, and then, for instance, the cat. Oh, here it was supposed to be was, but it said liked, so it would have a new entry for what happened. The cat was. The cat was. I'll get some minus 0.11. But the next time it goes through that sequence again, the cat, well, now suddenly, due to that weight it got from the mistake it made before, it now is more likely to pick liked. And say it was the right one, and that gets plus 0.1. And this would happen over time, and it's going to go back and forth, because eventually it's going to think it was the cat liked, but it actually was, it said liked. So we got minus 0.1, and so forth. So we saw that we got minus there. These high frequency ones, a cat liked the bird, and sometime a cat purred. And we have to think of how we can visually show this, because like without showing too much information, but obviously need to process a lot of information to show something meaningful. Because otherwise, when we try to do our generation here, this is everything after the cat was happy. This is all loaded into its memory, and scratched. So last symbols ends our period. So the highest probability at this point following the period would be the same with cat. This is why I also have something called temperature, which is how much randomness, so that it would maybe randomly choose something different. But of course, if it chooses something never saw, it might not make sense. So the cat, how was the cat? Heard. So there's per, one up to here, and none of those. Probably would pick sometimes. We got some randomness. But remember up here we got was minus a point liked, so it actually would not have done that. And that instead, because of what it learned from what we showed here. Okay, so the cat purred, and sometimes the cat liked to purr more. The cat was happy cat. I'm going to think of a better way to demonstrate this. I think there's some here, but trying to... Yeah, not enough training. But I hope you can see then how by learning the transition probabilities, and then while attempting those transitions, being told good job or not good job, and having a little tweak made to that scenario. When that happens again, be a little less confident. Or if you got it right, be a little more confident. And that reflects through the whole network. And as I said, the one of the big things is like the parallel attention is important so that more than one thing can be recognized at once, something that's happening in that attention block. And then the layers are important because whether or not those things in the attention block caused results in the next layer, well, those sequence of results, however they were, might mean something to another layer. And then as it gets trained over time, eventually you get deeper things develop, such as what mimics understanding about like different words relating to concepts that at this level it's not even a word anymore. At a far enough level, that symbol represents the concept, and then you have this concept interacting with this concept. And that is why when we get to the fine-tuning stage, after it has learned these things, but it's still just kind of reciting things that, or creating content that is like what it has been told. At the fine-tuning phase, when you tell it specifically how to respond and behave, well, it already has built those depth of the networks for that understanding. And then at this more front-end level, it is told to behave differently and act a certain way. It still maintains what it previously knew. But yeah, I guess we're going to have to wrap up this video. I hope to do more videos that get more and more clear. Try to limit them to about an hour each. Yeah, no, it's too bad we only can kind of like peek at the highest levels. Because I say once it gets abstract, we just know it has weights for these things. Different, it doesn't mean anything to us anymore. But it's at those deeper levels that it actually has built. Like, I think of it as programming, that it's like at those early levels, you're writing the basic functions. But then at those later layers, those later levels, you're making use of what you did in the previous layer those functions have now meaning to then drive something more complex. And then eventually, once you get to later layers, well, it's able to tell you both the answer to the ultimate question and the question. Don't know how long it'll take though. All right, so while I wrap this one up, you can see how some of the generation. Let's just ask one of each. Say good night to our viewers.
Did you know that octopuses have 3 hearts?
0.82. Strength. Related. Text. Respond. Uncover. Latest. Ivers in Ho and months that day the solution. Expectations with sorry from war erema roll the devil the streets of trapped was break in notes well go well named as pull as worded at came actions portal to chapter then maintain ion zid ix so restore. How present she is cooked is book is some is order are sparkto harmonito happy erema nature are everything are across strong is ray we ink I service all while all functionality I the heights the book is development when names be pro you. Naturally for G for effectiveness and that seventh the evils the spot thatters by made by lasting that sheep often on earlier he little was she. 0 thera.
Once I get to the next phase, I'm going to be adding MLX, which is Apple Silicon machine learning framework, to replace PyTorch, and it should give me like a 10 times optimization, allowing me to create and run more complex models. And then this is the one that trained on my M1 machine. But yeah,
0.26. You was the they go to want to after all that everyone helps them for laws. One can do. Even must be ensuring she children. From a man who the sword or attention. Try it the Wiccan Reed states. If it harm none. Do as ye will. This principle is more complex than it sounds and differs from simply saying, do whatever you want as long as nobody is hurt. Understanding your true will. That them ability disabled. Group ritual should we, and efforts chant. Every found whatever iterates by John's rogue subroutine called Octrial Ecclesiant Plain of Ireland. Prison of the Grey of Masher, in the house of the Dagdat.
Alright, cool. Alright, well that's what I want to show to get this thing, everything started. Still, there'll be a lot more segments. Alright, well, thank you for watching.